Okay, so the second major job the kidney has in maintaining acid-base balance is hydrogen ion secretion. So in the last video, we talked about bicarbonate reabsorption. Now we're talking about uh, acid excretion. Here's how it does it. So right now, what we're looking at, um, we're right here in the collecting duct. So cortical collecting duct and also medullary collecting ducts. In this segment, we have a type of cell called the alpha intercalated cell. So these cells are special in that they have these hydrogen ion pumps right here. These pumps use energy in the form of ATP to pump hydrogen ions out into the lumen. Okay, so where did these come from? Well, the same source that we saw in the proximal tubule. So dissolved CO2 and available water in the presence of carbonic anhydrase turn into carbonic acid, which will quickly dissociate into hydrogen ion and bicarbonate. And then these pumps can put the hydrogen ion out into the lumen. In addition to just being a standard hydrogen ion ATPase, there's also a hydrogen ion potassium exchanger. It's probably less important than the solitary hydrogen pump, but it's also present. As the hydrogen ion is secreted, also there's a chloride channel that allows chloride to be secreted along with it. So basically we're putting hydrogen ion and chloride into the lumen. On the basolateral side, you can see that there's a bicarbonate chloride exchanger. It'll bring chloride into the cell in exchange for putting bicarbonate into the blood. And so this is important, that just to note that whenever we're getting rid of one thing, like if we're getting rid of hydrogen ions, we're holding on to bicarbonate. And that's important. Every time we get rid of this, we're going to regenerate that bicarbonate to make sure that we don't deplete our serum source of bicarb. Okay, so here's a slightly different view, but we're looking at the same area. What I want you to consider is that after this hydrogen ions secreted into the lumen, it will affect the pH of the urine, but there is a limit to how low the pH can drop. The kidney can only acidify the urine to a pH of 4.5. And unfortunately, that only corresponds to about 0.032 milliequivalents per liter, which doesn't sound like a lot. Now, remember at the beginning of these videos, we said that on average, you produce about 1 milliequivalent per kilogram per day of acid just from your diet and metabolism. So that means, what, an average 70 kilogram person, remember they're going to make about 70 milliequivalents of acid per day. So if we were just dissolving hydrogen ion into the urine, we'd have to produce about 2,200 liters of urine a day. So obviously we don't do that. So we get around it by buffering. So we buffer most of this hydrogen ion in our urine. We have two main buffers. One is ammonia. The other is what we call titratable acids. But the major one is phosphoric acid. We'll go through these one by one. Okay, so hope you recognize where we are. We jump back into the proximal tubule, and the main reason why is because the proximal tubule plays a large role in ammoniogenesis. So this is the same proximal tubular cell we saw in the last video, but it can take glutamine, and it has the enzyme glutaminase, which converts it to glutamate and gives off one molecule of ammonia. And then glutamate is metabolized to alpha ketoglutarate, which produces another molecule of ammonia. The alpha ketoglutarate can actually produce more bicarbonate, which is then reabsorbed. But what's important is that all of this ammonia, so think about it, it's It's non-charged. It can actually diffuse across most of the membranes. Um, it diffuses into the urine, it can diffuse through the kidney, and it can make its way all the way to the cortical collecting ducts. Now here we are back in the collecting ducts. Here we have our ammonia, and this hydrogen ion that was just secreted can combine with the ammonia, and this creates ammonium, which is NH4 with a positive charge. And this process is actually called diffusion trapping, which is kind of neat in that the ammonia can diffuse across membranes into the lumen, but once it encounters this hydrogen ion, it forms this positive charge, which kind of locks it into the lumen. And the pKa of ammonium is so high that it's not going to give up this hydrogen ion easily. So once this reaction has occurred, it's going to stay in the lumen of the urine and trap it, which is very useful. For the titratable acids, like the phosphoric acid, hydrogen ion combines, and now this can be excreted in the urine. And also, a very tiny amount of hydrogen ion is dissolved, but the bulk of it was just consumed by these two buffers. And also, just to be complete, there is another cell called the beta intercalated cell. And it's kind of interesting in that it's basically the alpha intercalated cell just flip-flopped, okay? And I hope that's easy to conceptualize. On the apical side, we have this chloride bicarbonate exchanger, which it will get rid of bicarbonate, it will reabsorb chloride. On the basolateral side, it will reabsorb hydrogen ion and reabsorb chloride. This cell is most active in the setting of an alkalosis, where there's too much bicarbonate and we want to get rid of bicarbonate. So next, it's important to know what factors will stimulate distal acidification and which factors inhibit it. One thing to understand real quick is that the principal cell, which is also located in the cortical collecting duct, it has a sodium channel that reabsorbs sodium. It's called ENaC. And when it's extraordinarily active in the presence of sodium being delivered, it can produce a negative potential in the lumen of the tubule. So when the lumen is negative, that will provide a stimulus for hydrogen ion secretion by the mechanism we just went over before in the alpha intercalated cell. So things that will stimulate acidification if there's a lot of sodium delivery to this segment. So if there's a salt load or even exposure to loop diuretics, that will stimulate acid secretion. Also increased mineralocorticoid effects, so that will stimulate sodium reabsorption here, but it also directly stimulates the pump as well. So high levels of mineralocorticoid are seen in situations like excess renin-angiotensin system activation, exogenous corticosteroids, Cushing disease, even some types of licorice have a chemical that stimulates the mineralocorticoid receptor. But most importantly, acidosis. So acidosis will stimulate acid secretion, which makes sense. That's what we would want to happen. If you want to think about the opposite, things that will inhibit this system. So if there's decreased sodium delivery, there will be decreased acid secretion. So we need sodium and urine to flow by all of this to get these cells working the way they are. So if someone's volume depleted and there's low flow, you'll have decreased acid secretion. Likewise, decreased mineralocorticoid effects. Also decreased urinary buffers. So let's say you've lost the ability to produce the ammonia that I showed was necessary. That will reduce the amount of acidification that can occur. And also, if there's alkalosis, there will be less stimulus for acid secretion. Okay, now I'm going to summarize daily acid secretion to show you how all these concepts add up. One important concept, whenever you're losing hydrogen ion, you're at the same time gaining a bicarbonate ion. If you're losing a bicarbonate ion, you're gaining a hydrogen ion. I hope that's not too confusing, but the previous diagram should have explained that. Okay, so in your urine, the net acid secretion is simply just adding up some of the terms that we went over. How much ammonium was produced, okay, and how much of the other non-ammonia buffers, such as the phosphate. There are other proteins, even creatinine does a little bit of buffering. But I'll just use phosphate here as a titratable acid. And then, there's some hydrogen ion that is dissolved in the urine, and that's what directly affects the pH. So those will add up to give us how much net acid is being secreted, but also keep in mind if there's any bicarbonate that's lost in the urine. So if we're wasting bicarbonate in the urine, that represents a gain of hydrogen ions to the body. So I've added on approximate calculations for each of these values. So the amount of ammonium that's excreted is about 36 milliequivalents. The amount of titratable acid, the non-ammonia buffers, is about 35. The amount of dissolved hydrogen ion is actually pretty negligible. Remember, I said earlier at a pH of 4.5, that's only 0.032 milliequivalents. So yes, there's some, but it's not really a lot compared to the 70 milliequivalents per day that you have to deal with. And under normal circumstances, you reabsorb the vast majority of the bicarbonate that's filtered. And so maybe you'd lose like 1 milliequivalent of bicarbonate. So if we add all this up, it's pretty perfect. It comes out to be 70 milliequivalents, which is equal to that 1 milliequivalent per kilogram per day that's going to be produced just from metabolism and from your diet. And so if I could, just to bridge this to some clinical concepts real fast, this 1 milliequivalent per kilogram per day is going to occur as long as you're alive and you're eating. So what keeps you in acid-base balance and keeps your pH normal is the fact that all of this can occur in the kidney, and that obviously you're breathing and able to excrete CO2. But let's look at each piece individually and how it could possibly contribute to an acid-base disorder. The ammonia here, one interesting thing is that it's actually responsive to changes. So if you're developing a metabolic acidosis, the kidney can increase the amount of ammonia production, which can buffer more hydrogen ions. So this is adaptable by the proximal tubule. But you can also imagine a situation where what if the kidney is not able to make enough ammonia that it was able to? And this is what we see in chronic kidney disease, where someone has lost a number of nephrons. So if they were born with 100%, now if they have 20%, they can't make enough ammonia to buffer all the hydrogen ion that they're producing in a day. And this is what can lead to a chronic metabolic acidosis, just the inability to get rid of all the acid. What about some of the non-ammonia buffers? If the GFR is too low, it's possible they can't excrete all of these proteins or other buffers that they're normally able to, and that could diminish acid secretion. The actual amount of dissolved hydrogen ion is pretty negligible, so it's not really going to add too much to acid-base balance. But bicarbonate reabsorption could be a big deal in that what if that process of reabsorbing bicarbonate was affected? Remember I mentioned there's a chemical inhibitor, acetazolamide, which when given, it would increase the amount of bicarbonate lost in the urine, and that would correspond to a gain of hydrogen ions. We only use that clinically in the setting of someone has a metabolic alkalosis. But what if there was a problem in the kidney and you were unable to reabsorb that bicarbonate on its own and you're automatically spilling it? You could imagine if this number was higher, you could promote a metabolic acidosis. And we actually call that a proximal renal tubular acidosis, or RTA. But you'll learn about those later. Just trying to show you how some of these concepts connect to clinical scenarios.